So welcome in week 3 hydraulic engineering live TA session. Actually today I have I had the network problem, so that's why I'm going to record this video and I will upload it on YouTube. So let me put it the earphone. So please go through the video, and if you have any doubt regarding the today's session, please you can mail me. I Let me write my mail ID here. Small p. So this is my mail ID. If you have any doubt regarding this third week session, please write me mail about your queries. So we'll discuss in the further or next week in the fourth week. So the topic is about the laminar and the turbulent flow. So basically, before discussing about the laminar and turbulent flow, uh, let me discuss about some basic understanding. Then we'll further move on the laminar and the turbulent flow. So basically, this is a general information about the flow. So most of the flow, especially liquid, are transported in the circular pipe. Why? Why in the circular pipe? You have seen the most of the your liquid transported in the circular pipe. The reason behind it, why? Because here I have written, because the pipe with a circular cross section can withstand large pressure difference between inside and outside without undergoing sufficient distortion. So this is the main reason behind it, why we are using the circular section or circular pipe for transporting of the liquid. Now moving ahead, because of the it is able to withstand the large pressure difference between inside and outside of the pipe without undergoing the sufficient deformation. Now coming on the what about the non-circular. The non-circular pipes are usually used in application such as heating and cooling system of building where the pressure difference is relatively small. As you know, the pressure, atmospheric pressure is how much? Pascal. This is a huge pressure. But what is here written? The pressure difference is relatively very small. The manufacturing and the installation cost are lower and available space is limited for ductwork. So in this case, we will use the non-circular pipe if the available space is limited for the ductwork or the manufacturing and the installation cost is lower. So in such case, we will use the non-circular pipe. The efficient flow, what is actually these are point is very important. So let me tell you, circular pipes often the most efficient flow of fluid compared to other shape, the circular cross section minimize frictional losses. This is very very important. In the circular pipe, minimize the frictional losses, and how it minimize the frictional losses and how the withstand with the large pressure we will see in the further discussion. Allow for more streamlined flow. The result in less energy required to move the fluid as less pressure drop along the pipe, which is crucial for a long distance transportation. So I think you people got the efficiency of the pipe, that is the circular pipe. Uniform distribution. What is uniform distribution? In circular pipe, ensure a more uniform distribution of fluid across the cross section. If you see here in the circular pipe, more uniform distribution of the fluid, but not here because of this L section type of thing here, corner things you can see. So this help prevent the uneven pressure gradient. Throughout the section, the pressure gradient is same, but not in the case of if you talk about the rectangular duct. So this is the reason behind it, the why the pressure, it is the actually the even pressure distribution in the circular pipe, because of the cross section is very very smooth, there is no cone. Okay, now to ensure the fluid flow evenly throughout the pipe and reducing the risk of blockage of area of stagnant flow. So this is very important. And the structural integrity. The circular pipe have a natural shape that distributed stress evenly around the perimeter. This makes the structurally stable and less prone to deformation or collapse under the pressure, especially when compared to the shape like rectangular or square pipe. So these are the advantage of the circular pipe. That's why we use the circular pipe for, especially in case of liquid transportation. Here what is the figure is given is the your circular pipe, and here is your rectangular duct. You can see the circular pipe can withstand large pressure difference between the inside or outside without undergoing the significant distortion, but non-circular pipe cannot do this type of strip. So these are the some important thing. You please go one by one. Why circular pipe we prefer generally? So these are the advantages. So I think with this discussion, you might have some whatever your basic doubt about the why we use the generally the circular pipe, the reason behind it. These are the reasons. So now moving ahead with the velocity in the pipe, velocity distribution in the pipe. As you see here in the figure, your velocity distribution is like that. And how these velocities come in the pipe, or let me discuss more. This is the pipe wall. This is the pipe wall, and this one also. I think you heard about the no slip condition. No slip condition. When fluid particle, when fluid particle attached to any surface, by virtue of the fluid at the surface, the velocity of the fluid is zero. At the surface, velocity of the fluid is zero. And you know already the fluid having a property known as viscosity. Viscosity is nothing but the, if you I if I tell in the more generalized way, the viscosity is the friction in case of the solid, if you will correlate with the solid mechanics. So friction is nothing but the viscosity in case of the fluid mechanics. So what actually the mean, between the layer of the fluid, if we consider the water is moving in the layer form or sheet form, between the layer of the fluid, one force is opposing, try to oppose the above layer, and the above layer try to drag the drag in the forward direction of the lower layer. So this kind of thing is happen between the fluid layers. Okay, so what is here happening here, if I will draw a velocity diagram up to that. Okay, at that surface velocity is 0. Here the velocity is something little bit increase because it is above the this point and this point. At this point velocity or something increase. At this point velocity increase triple plus I want to write it. Okay, a little bit increase after that. But at that point what is working, at that point there is a two thing is working. What? Due to this roughness of the pipe, roughness of pipe wall, roughness of pipe wall, due to roughness of pipe wall, one force is try to oppose the flow, one force try to oppose the flow, that is the, you can say, if I will tell in the very layman point of view, that is the roughness, force due to roughness, force due to roughness of wall plus viscosity is also try to oppose the upper layer. But as we move in the upward direction, as we move in the upward direction, the friction force, that is your roughness force due to wall, is decreases. As the roughness of the wall decreases, what will happen? Your velocity little bit increase. Here all little bit above, your roughness of the wall increases, that is decreases, roughness of the wall decreases, so your velocity here little bit more. So similarly, goes up at the center of the pipe, your velocity is maximum, at velocity is your maximum at the center of the pipe, and your propagation of your roughness is very less or neglect or minimum at the center of the pipe. Similarly from this wall, but still you remember always, but still between the two layer, between these two velocity layer, your viscosity is working. Your viscosity, one layer try to, this layer, let's suppose this layer try to, above layer try to move forward, but this layer try to reduce. So this is working, but this is, but here additional, below this the additional force is working, what? Your roughness of the roughness force, that is the pipe roughness force, force due to roughness is working additionally. So here the velocity magnitude is reduced, very reduced drastically comparatively this, or reduced very high compared to this. So I think I am able to tell you uh, what is actually happening this velocity dive. Why near the wall is less? Actually, near the wall, the reason behind it, the less velocity is here, the roughness force. Now moving ahead. Here one thing is also important. Sometimes actually in every whatever you have seen the generalized formulas in everywhere, most of the undergraduate level, up to most undergraduate level, we use the average velocity, some correction factor, that is you know about already, the alpha and beta, using some correction factor, that is the kinematic correction factor and momentum correction factor. Using this correction factor, we use the always average, because at each and every point, that is the up, if you will analyze up to that much, the millions of the point is there, millions of the point is there, or more than the millions you can say. At each and every point velocity is changing, but if you will write this formula, like your discharge is equal to area into velocity. Here velocity is the average velocity. This velocity is average. Average means what? Here average, this dotted line is represent the average velocity. Means as you tell the velocity is average, this, that means what you are considering, you considering at the wall velocity is that much, but previously was what, your velocity was here 0, but as you averaging throughout the depth, your velocity up to that much, this velocity is come to that, this velocity is whatever the, this is ahead of this line, this red line, but it is limited to that, this 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 is limited to that. So this thing is reduced, and here we increase the velocity, that is your add, here was the 0, but we as averaging we adding something here, this is not 0. So for correct these things we use this alpha. Sometimes alpha value is 1 if we consider the, oh little, we'll talk about more about the when the alpha is 1 and all. Okay, so this is the qualitative i I was trying to tell about the velocity diagram in the pipe. Now moving ahead, the mass flow rate. This is very important concept in the conservation of the mass. Mass flow rate is okay. Let me actually try to tell you what is mass flow rate. The mass flow rate is nothing but okay. This is mass. If we tell about mass is represented by m. Here mass flow rate we are representing with the m dot. Mass flow rate, and formula is given what? Formula is given rho v average and is area of the cross section. This is the area of the cross section. If the pipe is circular, the area of cross section is this, pi r square you can say, or pi by 4 d square you can also say. Okay, so now what is actually this representing? If you will see what is mass formula, rho is equal to, you know already, m by v. So from here v means volume, from here m is equal to what? Density and volume. This is the formula of mass. So here if you will put rho into V, this is the mass, mass flow rate, mass per unit time, nothing but mass flow rate is the mass per unit time. Okay, if you will break these things, here you will write the T. If you will break rho into area into length divided by T, you will get what? Rho L by T is what? Velocity into area. So this term is nothing but mass per unit time. How much mass is flowing at a particular from a particular cross section with respect to time. Per unit time means, let's suppose if we consider that T is equal to 1 second, in 1 second how much mass is passing from this cross section, whether only 1 kg or 2 kg, 3 kg, whatever. So conservation of mass means what actually? Here what is actually written this equation 8.1, if you will see this equation, your mass flow rate is this one. The value of average velocity, the value of average velocity V average at some stream wise cross section is determined from the requirement of the conservation mass principle be satisfied. This means this much mass flow rate is going and this much mass flow. Actually what is written in the integration form, it is written like that. Your velocity is like your velocity is moving in the upward direction means what? Your if it is radius of the pipe, that is r, your velocity is function of r. So here this is written, your velocity is a function of r. So if we will correlate from here, at each point this term is written in the average form, this term is written in the form of your function form, that is in the function form and integrated over the area. So this should be equal. So the meaning is that here means actually the most appropriate expression for this is this one, because in this expression we have used what? Velocity is changing with respect to r. As your r is increasing, your as your r is changing, your velocity is changing here, but here we have written the average thing. So the general meaning is that if your mass flow rate is like, if we calculate the mass flow rate using the average, and if you will calculate the mass flow rate using this, both should be equal, then the mass of conservation law will be follow. So now we will come on the laminar and the turbulent flow. So these are the basic things, how your velocity diagram and why we use the circular pipe for the transport media. Now coming on the laminar and the turbulent. So this is very important also. Actually, for first 1 hour, I will tell about the concepts, and Then after we will discuss about some questions regarding uh, regarding the this today session. So actually the laminar, turbulent and transient, these three term is there. Laminar, turbulent and in between transient. Transient flow. If you will see here figure, here two example is there. One is about your pipe, that is the dike trace, and another example of the your candle smoke flue. So very interesting thing is here, if you will look this and this line. Below this line is laminar, above the turbulent flow, and in between is the transition flow. So if you will see, transition phase is very short term phase actually. In turbulent case, your smoke particle is very random motion is, but in case of laminar, your smoke particle is very smooth motion, not random motion, very smooth motion. That is the layer wise flow. What we have talked about earlier, that is the layer wise flow. One sheet flow on the above sheet, one sheet flow on the above sheet. This type of flow is the laminar. But if your flow is zigzag like that, if you will see here, this is the turbulent flow, this is the your laminar flow. So here pictorial representation. So these are the qualitative definition or qualitative understanding, or you will say, but uh, very general definition of the laminar, turbulent and transition motion or transition flow. But engineers always want to think quantitatively, not qualitatively. Qualitatively, anyone can say what is happening, but quantitatively, how much happening, and when we tell the laminar flow and when we tell the, because some mathematical thing should be, some mathematical formulation should be there, which gives the laminar thing and turbulent thing, whether the flow is laminar and turbulent. So Reynolds try to give, or Reynolds give the information about these things, whether the flow is laminar and the turbulent or the transition. So Reynolds try to experiment where when the flow is laminar, when the flow is turbulent, and when the flow is transition. We'll discuss about more. Here it is given. In this book, actually I am following the single Simbala book. So in this book, somewhere I have seen the sometimes written this value is given for the pipe flow actually. Pipe flow. If your Reynolds number is less than or equal to 2300, somewhere 2000 written, somewhere 2100 written, so this is also acceptable. So laminar flow. But in the exam, you generally use the 2000, because I have seen most of the places 2000 is used in the exam also. 23 to 24 greater than 4000, your flow is turbulent, or in between 23 to 24,000 your flow is transition. But now we will try to understand one important thing. What is RE? RE is nothing but it is the Reynolds. It is represent the Reynolds number. What is Reynolds number? Reynolds number is the inertia force or inertial force by the viscous force. Now it is very important one thing. What is inertia force and what is viscous force? This is very important. Inertia force is nothing but force due to, let me write, force due to inertia force. Inertial force due to mass and velocity. How much velocity and how much mass depend on that. So this is represented by inertial forces. Previously, what we have discussed already, your m dot is what? Rho V average into area of cross section. Here, what we are going to write, about the inertia force. Your inertia force, if you will see here the black box, what is written here, your inertia force is rho V square, that is V average square, and the L square. This is represent the inertia force. This is represent only the mass flow rate. Force is equal to what? Mass into acceleration, or you can say also rate of change of momentum with respect to time. Rate of change of momentum, that is not rate of change of momentum, also it is represent of force. So due to the mass and velocity, the inertia force is depend on these two things. So if you will write from here, what will happen? Already you have the mass flow rate, that is this one. These things you have, and one velocity term is come up with this. What will happen? This will rho V average square, that is this velocity, and already velocity is here, let, or AC square, AC. But in terms of length, I want to write in terms of length. So okay, go back. So rho V average square into area having the length, two length parameters, so L square. So this is written here. Now come on the viscous force. Viscous force is what? Due to the your viscosity. Force due to viscosity is represent the viscous force. Nothing but viscous force is what? Let me write here. Viscous force is shear stress, that is a force stress due to, if you will, what we know actually, we know the shear stress term. So always we try to du by dt So du by dy. So dy means what? The depth direction I am talking about. This is the x. So what is always we try to what we know, already know, we utilize that quantity for calculating the another quantity. So here we are trying to, and this force is why this shear force due to the viscosity. So here we use the these term. So stress formula is what? Force by area. So force means force is here what? This quantity into area. So let me put mu du by dy into area. So mu, this velocity is velocity average, that is y, and here y means L. I want to write here L because here I have converted the all area into your L section, that is your length parameter. So here y is also length parameter, here is a L square. Oh, this is cancel out 1 L. So mu u average L. So this is written here, and if you will divide one velocity, here the velocity cancel, and your L, 1 L cancel, rho v L by this, or v by rho you can write in the form of nu. Kinematic viscosity you already know about. Kinematic viscosity is what? Dynamic viscosity divided by rho. So this rho will come on this below part, and this will become as, so here it is written like that. Now come on the each term, each quantity of the Reynolds number. So rho is what? Rho is basically your the density of the flow. Rho is the density of flow. V average, velocity of the flow, average velocity of the flow. D, what is D? The characteristics length of the geometry. Characteristics length of the geometry. And what is characteristics length? We will discuss. Diameter. In this case, actually we are considering the pipe, so that is why here the, in this case, the diameter. And mu is what? Your kinematic viscosity, and nu is kinematic viscosity, and nu is dynamic viscosity. Okay. Also, kinematic viscosity has the unit of meter per second square and can be viewed as a viscous diffusivity or the diffusivity for momentum. Here, now we will correlate that your previous things, these things. Here I want to correlate your concept of the Reynolds number. Why the, let me write first, then I will discuss about. Re is equal to inertial force divided by viscous force. When inertial force will be more than viscous force. For the viscous force, let me write here the VIS. What will happen? If the inertial force is more, than the viscous force, what will happen? Or another case, let me take viscous force is greater than inertial force. In both two cases, viscosity is dominated in this case. If the viscosity is dominated, what will happen? Your Reynolds number in this case will be more. If I talk, if this is Re2, this is Re1. No, sorry. In this case, if viscosity is your more than this, your Reynolds number in case of 2 will be less compared to the Re1. Re1 viscosity will, Re1 Reynolds number will be more. So this is just qualitative understanding. Now come on the these two, whatever the number was written, 2300 and 4000. If your Re, this is also Re for a flow, any flow. This is also Re for any flow. Or here you little bit increase, here little bit reduce, that is 2 I have written here, and here I have written 1, 4100. For your understanding, just I am going to interpret something. So if these two things is given, and my question is that in which case in which case inertial force will be more. Can you guess in which case inertial force will be more? Whether R is equal to 2200 or R is equal to 4000. Obviously, from the previous interpretation, if you will see, a fluid is same. Please try to understand. Fluid is same in both cases. Cross section is same. Let's suppose water is flowing. That is, your viscosity is same in both cases. So in the first case, viscous force is dominated. In second case, that is this case, your inertial force is dominated. Means what? In this case, your mass flow rate, that is mass or velocity, what I was telling about previous, in this case will be dominated compared to this. That is the first one. So what will happen? What is here actually conclusion is that if your inertial force is more than your viscous force, if you will comparing two things, that is if you will comparing the means laminar and the turbulent, then that perspective I am going to talk about. It will be always more, because here Reynolds number is your 2002, then definitely in this case I will be more than viscous force. Here also I will be more than the viscous force, but more viscous force. That's why if you will divide something with the less quantity, that will give your maximum quantity. So that is in both cases maximum, but in we are comparing these two things, that is these two cases. So in which case I is more different, more dominated? So in the first case, that is your mass flow rate in the second, that is your second case, that the mass flow rate in the second case is very very high compared to first. If your inertial force is more, if you are comparing two things, more chances to flow become the turbulent. So here just the qualitative. If you will do self understand, if you will do your by your self understanding on pen and paper, then you will more easily understand. So what is the actually the characteristics length? Every time your pipe is not circular, sometimes square, sometimes rectangular, or sometimes channel also, open channel. So these characteristics length, how you will calculate? Actually for non-circular pipe, the Reynolds number is based on the hydraulic diameter, that is your DH, 4AC by P. P means what? Here P is the perimeter. Let me calculate for your circular pipe. 4 area is what? Pi by 4, pi by 4 D square. Perimeter is what? Pi D. Pi cancel, 4 cancel, D 1D cancel, only remaining D thing. So it is working for your characteristics length. So using this formula 4AC by P, you will calculate your diameter, calculate your characteristics length for the non-circular pipe. So in this figure given also, for a square duct A, for rectangular duct this perimeter is what? For rectangular duct this B plus A plus B plus A. So that is 2A plus 2B. So 2 is common here, so that's fine. So always remember, in case of open channel flow, it what is? That is weighted area by weighted perimeter. Weighted area is what? AB. This is the A, depth of the flow, and B is the channel width. Weighted area by weighted perimeter. So this A and this A, that is 2A, or weighted perimeter is B. This above here is nothing, so that is only B here. So always remember these things. Now moving ahead, the entrance region. What is entrance region? So hydrodynamic entrance region is what? Some equation is also given for calculating the entrance region. Sometimes you will maybe calculate. You just search out on the Google entrance region when the flow is laminar. That is the hydrodynamic entrance region. And when the entrance region, the flow is turbulent. Some quantity you will find it. Some equations you will be get. So entrance region is nothing but the it is actually length from where from your inlet up to that much length fully your velocity diagram is developed fully. That is after that your velocity will not change. Velocity diagram, okay. Velocity diagram will not be changed. If I will draw here, it will be similar kind of thing. The length of this, these are the equal. These all are equal. These all are equal. So after that not changing. But here if you will see, it is like that. Here it is a straight. Here little bit straight. Here little bit straight. Here not proper getting the shape of the velocity profile, but here you're proper getting the velocity profile. And this length, after how much length we will find out the velocity profile is fully developed. The lots of experiment is happened. So with that, this formula I think is given in the case of, if you will see, you can check also on the Google, actually the length of what length of hydrodynamic entrance region, or you can say also the hydrodynamically fully developed. After that, this this is the hydrodynamically fully developed region, and this is undeveloped region. So that's why we have hydrodynamic entrance region will tell. So always remember. Okay, now moving ahead. So here is the big pictorial representation. Velocity average always. So entrance length in case of laminar, you will calculate. If you will see here, entrance length if you will calculate by h, LH. So LH by D, your LH by D, and capital D, that is your diameter of the pipe, and this is equal to, this is calculated by these researcher in case of laminar flow. So you always remember, in case of laminar flow, your 0.05 RE into D. And I think your previous one was about in the turbulent flow. In the turbulent flow, the mixing during the random function, actually in the turbulent flow it is given like that. In the turbulent flow, some another researcher given this. So you remember these things. Sometimes the question come on that also, that point. So with this, now we will solve some questions regarding that. So this is the laminar and the turbulent flow. And I think in the your week 3, sir has discussed lot about the turbulent flow and the laminar flow. So these are the basic understanding. Now we will move ahead on the questions. Okay, the friction factor of laminar liquid flow in circular pipe is proportional to what? Your friction factor. Here we are talking about the friction factor. The friction factor, that is F, in case of laminar flow, the function of what? Function of what? Depend on what? Reynolds number, inverse to Reynolds number, square of Reynolds number, or the square root of Reynolds number. For calculating the friction factor, you just think 1 minute. You have the time for thinking. Think on this question. This is important. I think sir has covered these things also in the video class. Your friction factor, if flow, here the question is laminar, if the friction factor in case of turbulent, what? You heard about the Moody's diagram. What is the Moody's diagram? For calculating the friction factor in case of turbulent flow, we basically use the Moody's diagram for different your say roughness values of the pipe. Same Moody diagram, that is the modified Moody diagram. We can also use in the, and we'll use sometime in the open channel flow also. So in case of friction factor, in case of the laminar flow, you know always friction factor in case of laminar flow 64 by R. So it is depend only on the RE, or which is inverse of the Reynolds number. So option B is correct for that. In Hazen-Pausley flow of viscous liquid, one of the following pairs of the force strike a balance: inertial and viscous force, pressure and viscous force, gravity and viscous force, inertial and gravity force. Hazen-Pausley flow. Just please think on that. You have the 2 minute time on that. Try to think. This is also important. In Hazen-Pausley flow, Okay, please. Now I am come back. So sorry for the delay. So now moving on the next question. A flow in a pipe can be expected to be turbulent when the Reynolds number based on mean velocity in the pipe diameter is what? Is greater than 2000, equal to 0, less than 2000, greater than 3000, and greater than 4000, greater than 100. So in case of the pipe flow, here pipe is written. So as usual, you know already, your that is the 2000. Now this is also important questions. The stresses that arise due to fluctuations in the velocity component in the turbulent flow are what? What it is actually telling, your velocity, this is the mean velocity if you will tell about. In case of turbulent flow, your velocity is like that. So some fluctuations is there from the mean u dash, here below one u dash. Some fluctuations from by the mean, if you will compare by the mean. So what will it is talking about, due to the fluctuations, which type of stress in case of turbulent flow arises, whether the Euler, limit, Reynolds, and the principal stress. Just please think, within 1 minute you will try to give the answer of this question. So due to this, it is the Reynolds stress. You already know about Reynolds stress. V dash O plus. So I think in previous one I have not given the answer you. So for the Hazen-Fausley flow, the viscous liquid, one of the following pairs of the forces struggle. The answer of this question is A, inertia and the viscous force. Okay. Now moving ahead. The friction factor of the turbulent flow in a smooth pipe varies inversely as Reynolds number, directly as Reynolds number, as square of the Reynolds number, inversely as 1 by 4th power of the Reynolds number. So this is also important. The friction factor in the turbulent flow. Please try to give the answer of this question. Question number 5. If you will see the formula of friction factor, you will find out that it is the inversely proportional to of the friction factor is inversely proportional to Reynolds number. If you will see, but whether is 1 by 4th, whether is square, whether is directly, whether is what actually you try to find out. If you will try to search the formula of, in case of your smooth pipe, your formula of the turbulent, what I have seen here, your F is equal to, for a smooth pipe turbulent flow, 0.316 divided by Re to the power 1 by 4. For smooth pipe turbulent flow, not rough here, I am not talking about rough, 1 by 4. So option number D is correct for that. So next question is very interesting. Eddy viscosity. Eddy viscosity means that it is a physical property of fluid, same as the kinematic viscosity, always associated with laminar flow, and apparent viscosity due to turbulent nature of flow. So please think on that. You have the one or two here. Then I will discuss. Eddy viscosity means that after these question I will show also the previous year hydraulic engineering NPTEL assignment questions. So for that, actually, it is a apparent viscosity due to turbulent flow, not as a same as kinematic viscosity or kinetic viscosity. So option D is correct for that. Which of the following represent the major losses, that is the bend in the pipe, fitting in the pipe, sudden expansion, or the friction losses. The major loss. Try to think on that. Question number 7. Which of the following represent the major energy losses? Bent pipe, pipe fitting, sudden expansion, friction losses. So major losses actually due to the friction losses. Bend in pipe, pipe fitting, sudden expansion. Due to these cause in the pipe, these are responsible for the minor losses in the pipe, but friction is the major loss. So I think you remember about the formula also. The head loss, that is your friction head loss due to your friction of the friction losses. There is pen. So a head loss, that is HF is equal to V square by 2ZD in the circular pipe. So these are the equation. Okay. Now the hydraulic gradient line is the sum of pressure head, datum head, and the kinetic head of the flowing fluid in pipe. This statement is true, false, or can't say. Please try to give the answer of this question. Actually, try to give the answer of this question self. So I will wait 1 minute, then I will give the answer. So the answer is this question. Let me discuss about more. Let me drawing these two things. So let us suppose one pipe is let it down and water is flowing like that. If your datum is here and this is the center line of the pipe, if you will insert some piezometer here and here, some suppose here the height in the pipe is this, up to that much. In this pipe, little bit lower because of the friction losses. Suppose here, and this is your datum at that point, Z1, here Z2, this is height. Suppose I will tell you, okay, we assume that this height is y2 and this height is y1. But this is what actually the P by rho g. Okay. So if you will connect these line, this represent what? If you will connect these line, these from here to here and from here to here, if you will connect these 2 points, this line give you the hydraulic gradient line. Above this one imaginary line, that is your, this imaginary line due to your kinematic, that is the kinetic energy, that is the energy due to flow, energy due to velocity. So let us suppose here and here. So this is also connected here also. So if you will connect these whole length, this is whole total from datum to up to that much, or this your is the v1 square by 2g, this is your v2 square by 2g. So this will give you what? Energy gradient line. And here your hydraulic gradient line is the sum of datum head plus pressure head, and your energy gradient line is the sum of what? Datum head, pressure head plus velocity head. So here what is talking about? Hydraulic gradient line. Hydraulic gradient line is these two things only, datum head and the pressure head. But here kinetic head is also written, so this is wrong. Statement is wrong, so false. So this is the whole idea. Now this is again formula, you can go through the formula. For a study in question number 10, the study in compressible flow. Flow is steady and incompressible through a closed conduit of uniform cross section. The direction of flow will always be from higher to lower elevation, from higher pressure to lower, from higher to lower velocity, from higher to lower piezometric head. Which one is correct? In case of pipe flow we are talking about, not the open channel. In pipe you always remember flow is pressurized. So this is the hint of this question. Based on this hint, the flow in the pipe is pressure flow, pressurized flow. Now give the answer of this question. For this question you have the 1 or 2 minutes, please. So now we'll talk about. So actually in the pipe always the pressurized flow, So in pipe, not depend if your pipe is like that. If you will measure the height from here, level is here Z2. So Z2 is greater than Z1. So it not means that your flow will from here to here. It may be the flow from this side to this side. If the pressure is here more, P1 and P2, if this is P2, if P1 is greater than P2, the flow possible in this direction. If P2 is greater than P1, flow possible in this direction. So from higher to lower pressure, flow will happen in the pipe walls. But in case of the open channel, it is from higher elevation to it, because here the game is slow. The water is flowing by slope, not any other the external pressure. Here we are provide the pressure in the by the external pump or motor, you will say. So but in case of open channel, always flow due to gravity or slope. So from higher, if you will draw a horizontal line, so here is the height is more, here height is less, so water will flow from this side to this. Always remember. So again, this is the formula. Always know that RC's head loss formula is what? 4FLV square by 2GD. Based on that, you will calculate. So now we will move ahead on the your previous year assignment question of hydraulic engineering. Week 3 actually we are talking about. Just wait few minutes. File will be open. Today actually I was have the network problem, so that's why we are recording this time, and I will upload this video. If anybody have the question, please, on the first slide of my PPT I have written my actually the mail ID. On that mail ID you will write me your queries, then we will discuss about it the next class or coming for you. So this is the question of previous year hydraulic engineering assignment week 3. So based on this assignment, you will think about this semester also assignment will like that similar. So first question is that the Bernoulli equation is applicable between any 2 points. The option is in any rotational flow of an incompressible fluid, in any type of irrotational flow of fluid, in steady rotational flow of an incompressible fluid, in a steady irrotational flow of an incompressible fluid. Please think on that. This is the important, very very important. Basically, question from the assumption of what you have taken the assumption during the your derivation of the Bernoulli's equation or Euler from Euler to Bernoulli's. So here you will think. So which option? Option A, B, C, D is correct. Please think. Give your answer within Just self answer. Give the self answer 1 or 2 minutes. Just think which option is correct, and I will give the answer. Okay, logically you think. So option D is correct. Flow should be steady, rotational, incompressible fluid. Then we can apply it. Now moving ahead on the next question. The assumption of the given here. So question. A siphon used to empty a tank consists essentially of a pipe with its summit 0.5 meter above the water surface of the tank and its outlet of 2 meter below the summit. Neglecting the frictional and other losses, the velocity in the siphon is what? Please read the question carefully, draw the figure, then we'll approach what is asking. So in this question, velocity in the siphon is asking about. Please try to solve. Please try to solve, then I will show the answer of this question. You have the 2 minutes for that question. Okay, now I will show the answer of this question. Actually, the head difference is what? 1.5 meter. So velocity is what? Root 2 gh. Hence the velocity in the siphon is root 2gh. And this is come on the basis of what? The Bernoulli equation. Here is the atmospheric pressure. If you will, if I write P atmospheric, at this point and this point we will apply the Bernoulli's equation, P1 by rho z plus V square by V1 square by 2z plus Z1 is equal to P2 by rho z plus V2 square by 2z plus Z2. So this is cancelled because atmospheric pressure is same. Here the Z1 is what? If you will consider the datum this point, what will be the for Z1 is how much? If the datum is this, that is Z2 is equal to 0. Z1 is how much? This height 2 minus 0.5, 1.5. So here 1.5. Velocity at point 1 in the tank is 0. V1 is equal to 0. So what is remaining here? That is Z1 is equal to V2 square by 2g. Z2 is already 0. So V2 square by how much? Z1 2g. So Z, if we will cancel out, V2 is how much? Z1 2g. Z1 is 1.5 2g. So we will calculate, and u2 is the velocity of what? This is your point 2, ut is the velocity of in the pipe. So if you will calculate root 2gh, here h is equal to nothing but z1. So this is based on that. Now coming to question number 3. In a flow of a real fluid, with no addition of energy. Option A, the energy line will be horizontal or sloping upward in the direction of flow. The energy line can never be horizontal or sloping upward in the direction of flow. The energy line will be horizontal or sloping downward in the direction of flow. The energy line can never be horizontal or sloping downward in the direction of flow. In real fluid with no addition of energy. This is not the case of ideal fluid. Don't confuse from the ideal. In ideal fluid there is no viscosity, but here we are considering the viscosity. In a flow of a real fluid with no addition of energy, please think on this question and try to give the answer. Whether A, B, C, D, which one will be correct? Think. Real fluid means what? Your viscosity will be there in the pipe, in the fluid. So option C is correct. The energy line will be horizontal or sloping downward in the direction of flow. Discussion, what is detailed solution of that? If you will see detailed solution, for ideal or non-viscous fluid, there are no laws. Hence, total energy line, that is TEL, for that fluid is a horizontal line. But for the real fluid, it will always slope down in the direction of flow because the energy must decrease in the direction of flow. So it will be the downward. The energy line will be horizontal or sloping downward in the direction of flow. Question 4 is what? Okay, answer is this, but how we will calculate? This is very important. A fluid of viscosity 12 poise and specific gravity 1.2 is flowing through a circular pipe of diameter 100 mm. The maximum shear stress at the pipe wall is 240 Newton per meter square. Find the pressure gradient in Newton per meter square per minute. So this is also important. Please try to solve this question. So if I show the answer, so viscosity of the fluid was 12 twice, specific gravity is 1.2 was given. So the mass density is specific gravity into the standard density of standard fluid, that is 1000 of water. Diameter of the pipe was given already, 0.1 meter, and the maximum shear stress was also given, 240 Newton per meter square. The question was the pressure gradient. Gradient means what? As your fluid is moving in the forward direction, that is x direction, if we be talking about the one dimensional, so how the pressure changes. So formula is what? Your tau naught, that is the maximum shear stress, is equal to minus rate of change of, that is your partial derivative of pressure with respect to x into r by 2. So if you will put the values of all given datas, you will get minus 9600 Newton per meter square. So this is the whole idea. Now the dimension of kinetic energy correction factor. Here is the correction factor, kinematic correction factor, what I was talking about previously in the PPT. Alpha and beta, here alpha is there, the kinetic energy correction factor, the dimension of this. So actually it is a dimensionless. We will go through the detailed things. Alpha is nothing but the kinetic energy per second based on actual velocity divided by kinetic energy per second based on average velocity. So both above, that is the numerator and the denominator part, is the energy, so it is cancel out the times. Now coming on the next question, question number 6. Two parallel plate kept 200 apart above apart have a laminar flow of oil between them with a maximum velocity of 2 meter per second. Maximum velocity. Calculate the discharge per meter width. Assume viscosity of the oil is 24.5 poise. Calculate the discharge per meter width. Yes, please. Discharge we calculate based on what? Average velocity or maximum velocity? You think on that. Whether we calculate discharge on average velocity or maximum velocity. So here in the question is given the maximum velocity. If discharge is calculating based on the average velocity, first you need to calculate the average velocity, then we go ahead with your basic knowledge about the formula of discharge. So please try to solve within 2 minutes, then I will show the question, the answer of this question, question number 6. So now we will go on that. So first we calculate the average velocity, that is, it is well known formula, average velocity 2 by 3 of the u maximum, so 1.33, and based on the this you will calculate the discharge per unit width. What is actually discharge per unit width means? Velocity discharge, actually the formula of discharge is what? Discharge is equal to area into velocity. This velocity is average. So here you have calculated the average velocity, but here talking about the discharge per unit width. So that is discharge per unit width. So discharge is area into velocity average. So here is what? Y into B. So B we cancel, only remains the Y. So Q is equal to V average into Y. So here the depth of the flow was given, I think 0.2 in the question, if I am not. Yes, distance between the parallel plate. Distance between the parallel plate, here it is written by small b. So this is 2, or if I am talking about depth, if it is considered the y, so just multiply and get. Now the same question is here. what we are talking about the first question in the previous. The viscous flow of For viscous flow, the friction factor is given by 8 by Re, 64 by Re, 16 by Re, 32 by Re, 64 by Re. Friction factor he is talking about, not friction factor. So it is 64 by Re. Question 8. When a steady two-dimensional jet of water impinges on a stationary inclined plate, this is the stationary inclined theta inclined two-dimensional jet of water, and if the fluid friction is neglected, the resultant force of the plate is what? Tangential to the surface, normal to the surface in the direction of flow, normal to the direction of flow. Here what one thing is written, fluid friction is neglected. This is the twist in this question. The fluid friction is neglected. Then your resultant force on the plate is what? Tangent to the surface, normal to the surface, in the direction of the jet, normal to the direction of jet. Please think, then I will show the answer. You have the 2 minutes for that. Okay. So the answer of this question is normal to the surface. Why? When a steady two-dimensional jet of water impinges on a stationary inclined plate, if the fluid friction is neglected, the resultant force on the plate is the normal to the surface. Okay, not on the inclined to the, not on the tangential, because of the what? we have here neglect the friction. The shear stress developed in the pipe containing water is 4 Newton per meter square. What is the shear velocity in circular pipe? We are talking about the shear velocity. So this is also one important velocity. Shear velocity talking about. Shear velocity. Shear stress is this. So if you know the formula of shear velocity, you can calculate easily. Sometimes it is written in the form of, if I give you hint, u star root under some quantities here and here. Please solve within 1 minute. Okay. So the answer is shear velocity here is represented in this question by F. So tau by rho. So that is 4 by, this is whole, these two term in the under root. So it is, if you will calculate, these things will come out. Now question number 10. Question number 10 is the equation of motion for the laminar flow of real fluid are known as Euler, Bernoulli's, Navier, Hazen-Pawlowski. The equation of motion for the laminar flow of real fluid. Here we are talking about real fluid. That is your viscosity considered. Try to think. That is your Navier-Stokes equation. So option C is correct for that. Now moving ahead, question number 11. So shear stress in turbulent flow is due to what? The viscous properties of fluid density, fluctuation in the velocity in the direction of flow, and the fluctuation in the velocity in the direction of flow as well as transfer to it. So please, you always think about when you select the, when you solve the objective kind of thing problem, you always remember one thing. Try to select the best appropriate option. It may be the one option is correct, one it may be the option is partially correct, but which one is the best suited or best accurate, best near to the accurate, which option is. If you have the one option, you need to the select only one option, then this is the rule. Which option is the best appropriate answer for this question? It may be the partially correct, it may be the very near to the correct. So please always remember. So think in mind and try to give the answer of this question. Okay. The option number D, the fluctuation in the velocity in the direction of flow as well as transfer to it. The shear stress in the turbulent flow is due to this fluctuation kind of thing. Now question number 13, head loss through the fluid flowing in pipe due to fraction is. Oh, previously we are talking about the question which one is the measure loss in that question, in the previous question. The option was about like that, the pipe elbow, pipe fitting, and so and friction. In this question, just opposite. Just try to think. That previous questions was of the fluid mechanics, that is the course of fluid mechanics NPTEL, and this question is the previous year hydraulic engineering question. So maybe you can think about this type of question will come in your coming assignment or in the final exam of the NPTEL fluid mechanics. So head loss through the fluid flowing pipe due to the friction is minor, major and both. So it is due to major loss. It come under the major loss, not minor. So what is the description is there? If you will read, the head loss through the fluid flowing in the pipe due to friction is major loss, and the minor losses are those which are caused on account of total disturbance produced by such as fittings and valves, bends, etc. So these are the some important questions regarding that and the concepts. If please anyone having the doubt regarding that, today's session is due to the network problem. I have not able to live streaming of this session, so that's why I recorded this session from 9 to 11. So I will upload on YouTube. Please go through the session and give your comment by, or you can mail me. I have written the mail ID here. I want to also, if you will tell, the OPMAURYAIIT 40@gmail.com. So this is the my mail ID. Oh, sorry. So this is a mail ID. If anyone want to have any doubt, please write. We'll discuss on the next. Okay, thank you. We'll meet on the next Monday. Hopefully everything will be fine that day.